Greetings, physicists. My name is Greg, and today I'll be deriving the Euler-Lagrange equation. The Euler-Lagrange equation is a very powerful equation in classical mechanics and in calculus of variations. And using the Euler-Lagrange equation, if you have a function known as the Lagrangian, which is simply a system's kinetic energy minus its potential energy, you can plug it into the Euler-Lagrange equation and get that system's equations of motion. So very, very powerful stuff in the world of physics. The Euler-Lagrange equation can be derived in two main ways. The first way is using a principle known as D'Alembert principle, but that way is very involved when compared to the second way. I might do that in a future video if you're interested. But for the second way, which is what I'll be doing in this video, you use a principle known as Hamilton's principle. Hamilton's principle states that for an object's true path, the variation of the action will equal 0. And the action is a functional, which is defined as being the time integral from time 1 to time 2 of the Lagrangian of the system. With the Lagrangian, of course, being a function of a generalized coordinate q, a generalized velocity q dot, and time. Now, the history of Hamilton's principle is quite fascinating. It all started from a very old variational principle called Fermat's principle. And this principle is a principle in optics that says that light in a medium always travels the path of least time. This then inspired a physicist named Maupertuis. And Maupertuis, he saw this and he thought, well, if there's a variational principle for optics, then why not one for mechanics? And he came up with a principle of his own called Maupertuis' principle. And Maupertuis' principle is basically like a special case for the principle of least action. And Maupertuis' principle eventually evolved into the modern Hamilton's principle once Sir Hamilton came into the scene. So for a full breakdown of this history, I'd really recommend the very excellent Veritasium video about Hamilton's principle. And in that video, he talks all about how Maupertuis, basically, his work led to the evolution of Hamilton's principle. And it's very, very well done. I'll put a link to it in the description. Now, before we get into the derivation, let's talk about variations. So suppose we have an object which starts at point A and travels some path, we'll call this path 1, to get to point B. Now, this path, whose displacement we'll refer to as q, is the true path that the object traveled in order to get from point A to point B. But to get from point A to point B, the object could have taken path 2, or it could have taken path 3, or path 4, or an infinite number of paths. As long as the object starts at A and ends at B, all of these paths will have the same displacement from the starting point and the end point. Now, in calculus of variations, when we refer to a variation, we're referring to the hypothetical value of a variable. So when we refer to variation in displacement or virtual displacement, we're referring to all of the possible ways that an object could have deviated from its true path. So all of these deviations from the true path, these hypothetical paths that the object could have traveled, will be denoted as q plus lowercase delta q. And lowercase delta usually refers to variation. So we're referring to these paths as the displacement plus the virtual displacement. So we're saying that these paths deviated from the true path by some virtual displacement. The Lagrangian of the true path is a function of variables q, q dot, and t, where q is the displacement, q dot is velocity, and t is time. Likewise, the Lagrangian of all of the possible paths is equal to the Lagrangian of the true path plus some variation in the Lagrangian, where variation is denoted by lowercase delta. So here we have the variation in the Lagrangian. And this is equal to a Lagrangian whose variables are q plus delta q, q dot plus delta q dot, and t. This means that the variation in the Lagrangian is equal to the Lagrangian of the hypothetical paths minus the Lagrangian of the true path. Now we know all we need to know about variations. Now let's move on to the derivation. We start with Hamilton's principle, which says that for the object's true path, the variation in the action is equal to 0. And the action is a functional, which is defined as the time integral from t1 to t2 of the Lagrangian of the true path. So this means that the variation in the action is also equal to the time integral from t1 to t2 in the variation of the Lagrangian. And as we discussed previously, the variation in the Lagrangian is simply equal to the Lagrangian of the possible paths minus the Lagrangian of the true path. We can then use Taylor series to get a first-order approximation of the Lagrangian of the possible paths. So using Taylor series, we get that the first-order approximation of the Lagrangian of the possible paths is the Lagrangian of the true path plus the partial derivative of the Lagrangian with respect to q times the variation in q plus the partial derivative of the Lagrangian with respect to q dot times the variation in q dot. So we can simply rewrite this Lagrangian as a first order approximation using Taylor series. So let us do just that. If you'll notice, since the Lagrangian in the approximation, the Lagrangian of the true path, is equal to this Lagrangian but has an opposite side, those two will just cancel out. So what we'll get is then the partial derivative of the Lagrangian with respect to q and the variation q plus the partial derivative of the Lagrangian with respect to q dot times the variation in q dot, and then integrated over time. We can split this integral up into two different time integrals just for ease of manipulation. And we can evaluate this integral using integration by parts. If you remember from calculus, integration by parts says that for an integral from a to b, where the integrand is u dv, this is equal to u times v, evaluated from a to b, minus the integral from a to b, where the integrand is v du. So we can simply use integration by parts to evaluate this integral. And let's do just that. So in this case, our u is going to be the partial derivative of the Lagrangian with respect to q dot. And our du will then be the time derivative of the partial derivative of the Lagrangian with respect to q dot times dt. Now our dv will be the variation in q dot, and our, of course, this is times dt. And our v will then be the variation in q. So now let's use integration by parts. So rewriting this first integral, and then evaluating the second one, we have our u is right there, and then our v. So we have the partial derivative of the Lagrangian with respect to q dot times the variation in q, and this is evaluated from t1 to t2, minus the integration from t1 to t2, and our du is this term and our v is this term. So I'm going to write du first. So we have the time derivative of the partial derivative of the Lagrangian with respect to q dot times the variation in q, and then dt. So since this is being evaluated from t1 to t2, the variation in q won't change along this interval. So we can just get rid of this. So this will just equal to 0. So then that leaves us, and we can put this all back into one integral again. That leaves us with the partial derivative of the Lagrangian with respect to q minus the time derivative of the partial derivative of the Lagrangian with respect to q dot. And this is all being multiplied by the variation in q. And if you remember from Hamilton's principle, which says that for the true path, the variation in the action must equal 0, this whole integral should just be equal to 0. But the only way that is true is if this integrand is equal to 0. So in order for Hamilton's principle to be true, the integrand must also equal to 0. So we can just, let's see, I'll write it over here. And then this is all being multiplied by the variation in q. And that whole thing is equal to 0. So all we need to do is just we divide the variation in q by both sides. And then we get, spectacularly, our Euler-Lagrange equation. So there we have it. We have just used Hamilton's principle and derived the Euler-Lagrange equation. So thank you all for watching. I hope this derivation was helpful, or you at least found it somewhat interesting. I'm planning to make a series out of this where I derive something new every Friday. So thank you all for watching. Please leave your questions or comments down below, and have a great day.